Okay, this is the Unit 9 Study Guide Answer Key. Basically, what I'm going to do is I'm going to work out all of the problems from the study guide. Okay, first part of the study guide, well, is the vocab. You have to know the definitions, mainly those 10 that are in the back. I told you before, there are definitely going to be some of those are on there. It's a little matching thing, so just make sure you know those 10. Okay, the second part is pressure conversions. So, now if you look at number 1, it says convert the following to atmospheres. So the first one, 1A, is 311.8 kPa. Now, when we're doing the pressure conversions, this is where we use our little picket fence. So, in here, now, we've got kPa to atmospheres. So we're going to put the kPa on the bottom, and we're going to put the 1.0 atmospheres on the top. Okay, and 311.8 divided by 101.3 is 3.08 atmospheres. Okay, and let's do B. We're starting out with 897 millimeters of mercury. Okay, we're going to put the 760 millimeters of mercury on the bottom with 1.0 atmospheres on the top, and it's 1.18 ATM. Okay, so far so good, I hope anyway. Okay, now we're going to do C. This is still 1C. It's 10.5 PSI. Now if you have not written down the PSI on there, because it's on that sheet, I didn't include that. But you may need to know it. I think I do have one problem where you have to worry about PSI, so I would put down the PSI one too, and that's 14.7 PSI is also 1.0 atmospheres. Okay, and then that answer is 0.714 ATM. Okay, now number 2, it says convert the following to kilopascals. Okay, so we're going to convert from whatever it gives you to kPa. So the first one is 2.17 atmospheres. We're going to put 1.0 atmospheres here, and we're going to put 101.3 kPa here. Well, this is 2.17 times 101.3, and that gives us 220 kPa. By the way, just go to 3 sig figs, 3 numbers, period. Because 220 really only has 2 sig figs, but if we just go to 2 numbers, I'm not going to hold you accountable for the sig figs on the pressures. As I said, just make sure you have 3 numbers there. All your answers have 3, you're fine. Okay? Okay, so we did 2A, now let's do 2B. And we start out with 683 millimeters of mercury. And so we're doing 760 millimeters of mercury. We're 101.3 kPa. And we get 91.0 kPa. And then C, 39.7 PSI. So we put the 14.7 PSI on the bottom, 101.3 kPa, and we get 274 kPa. Okay, hopefully you guys can handle all the pressure conversions. Okay, next is the gas laws. And I pretty much tried to go in order, so we should start out with Boyle's law, then Charles' law, then Gay-Lussac's, then Avogadro's law, then ideal gas law, molar mass, and then density. Okay, so on the test, am I going to do that? No. So you've got to be able to figure out, and as I go through this, I'll give you clues as to how to figure out what law it is. Okay, so let's look at number 3. Number 3 says a 31.8 milliliter sample of gas is at 806 millimeters of mercury. Well, right now, if you see milliliters or liters, it's a volume. So we have a volume, and that's at 3.18 milliliters. Now, I don't know if it's a V1, P1 type of stuff. I'm just going to put the 1 down. You don't have to. You could actually just put the V down and add the 1 later. In fact, let's do that. And then the next one is 806. So we have a pressure of 806 millimeters of mercury. Now, if the pressure is lowered, okay, so right now I know I've got another pressure. So I can put my 1s there. So I'm going to go ahead and write the V2 and P2. So if the pressure is lowered to standard pressure, well, standard pressure is 1.0 atmospheres, but we're in millimeters of mercury. So if you remember, all of those things are equal. So our standard pressure is 760 millimeters of mercury. Okay. What is the new volume? So I'm looking for the volume. Now, this is Boyle's law. It's got P's and V's. So if you remember, this is V1 P1 equals V2 P2. And then I went ahead and worked out all the different equations. So we're going to solve for P2. So P2 is V1 P1 over V2. Okay? That's the equation we're going to use here. So now we're just going to plug and chug. So P2 is 3.18 times 806 divided by 760. And when we do that, we get 33.7 milliliters. Okay? And it makes sense. And double check. Remember, with this one, if you increase the pressure, you should decrease the volume. If you decrease the pressure, the volume should increase. So here, we had a decrease in pressure, which means our volume should have increased, and it did. Okay, let's look at this one. Okay, number 4. A sample of gas has a volume of, I'm going to write the, no, actually, move back, wait for back. I'm going to write the V equals, and it is 0.515 liters. If the volume is decreased, so now I have a V2, so that was my V1. Ooh, 223 milliliters. Now, here's the thing. I've got 2 different volume units. I can't have that. So I'm going to go ahead and convert this to milliliters. Now, if you look at your sheet going from liters to milliliters, okay, you multiply by 1,000. So this is going to be 515 milliliters. Now, then it says the pressure is 0.819 atmospheres. What is the initial pressure? Okay. Now, if you're not sure where to put that pressure, 0.819, well, look at the next, well, look at the question, the next sentence, or just think about it. The 223 milliliters is connected to the 0.189 atmospheres, so it has to be 2. So my equation actually is P1 equals V2 P2 over V1. So P1 equals 223 times 0.819 divided by 515, and I get 0.355 ATMs. Okay? Pretty easy, hopefully anyway. Okay, number 5. It says a 120 milliliter sample of helium, so I don't have a volume. 121 milliliter sample of helium is at 35 degrees Celsius. Well, that's a temperature. Now, remember, we don't ever put Celsius in here. So this one you can write down. Now, one of the kids in 3rd period, Emily Martis, she liked to do this and then the slash and write the 308K. That's perfectly fine. In fact, that's pretty good. That way you know that, okay, 35 is what the original was, and 308K is what I'm going to use in my equation. So that's actually not a bad idea. So thank you, Emily. Okay, so it now says if the volume is increased, so I have another volume. So I'm going to put the ones here. Volume is increased to 200 milliliters. What is the new temperature? Now, I will tell you, this one's obvious that you need Celsius. Later on in some of these, it's not going to be so obvious. Unless I specifically ask for the temperature in Kelvin, always use Celsius at the end. So you're going to have to calculate in Kelvin and then convert to Celsius. Okay, I always want my temperatures in Celsius at the end. So you need to convert back to them because we don't ever use Kelvin in real life. Okay, so now this is, of course, Charles' law. So we're going to do 121 over 308 equals 200 over T2. Cross multiply and divide. So you get 200 times, now remember, you don't have to write this part. I'm just doing it to show you. And I get, what is it, 509 K. Now, to go from Kelvin to Celsius, I have to subtract 273. When I do this, I get 236 degrees Celsius. Woohoo, that's hot. 100 degrees Celsius is boiling temperature for water. We've really made this gas hot. Okay? So, not too bad. Okay, number 6. A sample of gas is stored at standard temperature. So we have a T. Standard temperature, of course, is 0 degrees Celsius or 273 K. And then it says, if the temperature is increased to 20 degrees Celsius, so that's a T1, so now I got to have my T2, 20 degrees Celsius, which is 293 Kelvin. Okay. The volume increases to 125 milliliters. 125 milliliters. And then it says, what was the initial volume? So even if you didn't realize that the 125 was the second volume, the question next asks, what's the initial volume? Remember, the initial is the first one. Okay? Now, I know I've written this backwards, but we can still put it into our equation. So it's going to be V1 over 273 equals 125 over 293. Cross multiply and divide. So we get 125 times 273 over 293. And when we do that, we get 116 milliliters. And that's our new volume. Okay, number 7. A sample of hydrogen gas is stored in a container under STP. STP gives me a temperature and a pressure. So I'm going to put the temperature, 0 degrees Celsius, or 273 K, and pressure. And I'm going to use 100 atmospheres. Okay. Now, if the pressure is increased, oops, looks like our pressure is in, so we got a 1 and a 1. Pressure is increased to 205.4 kPa. What's the initial, or what is the temperature? So we don't want ATMs, we want 101.3 kPa. Okay? So now, this is now Gay-Lussac's law, pressure and temperature. So it's going to be 101.3 over 273 equals 205.4 over T2. Okay, cross multiply and divide. You get 205.4 times 273 over 101.3. And when we do that, we get 554 K. Now, we want it in Celsius. Told you all my answers, unless I specifically ask for the temperature in Kelvin, you want them in Celsius. So it's 281 degrees Celsius. Now it's also pretty warm. Okay, so that's that answer. Okay, number 8. A sample of hydrogen gas is stored in a container that has a pressure of 315 atmospheres. If the container's temperature and pressure are lowered, okay, so it's a P1, so P2 and T2. So let me back it up. Okay, if the container's temperature and pressure are lowered to STP, okay, standard pressure is 1.00 atm, of course 0 degrees Celsius or 273 Kelvin. What is the initial temperature in degrees Celsius? Here I even specifically said degrees Celsius, but whenever I'm asking for temperature, as I said, unless I specifically ask for Kelvin, it's in Celsius. Okay. So it's 3.15 over T1 equals 1.00 over 273. So this is 3.15 times 273 divided by 1.00. And when we do that, we get 860K. 860, oops, that's a 6. Minus 273 equals 587 degrees Celsius. Okay, that's pretty warm. Probably not going to find that in any regular laboratory, but what the heck. Okay, number 9. 12.5 grams of helium gas. So that could be an M or an N. Let's continue on before we label it as such, because I mean, if you didn't know that this was going to be Avogadro's law, and you're just looking at the test, it could be an M, which is the little mass, remember, with the molar mass and density equation, or an N. So let's read on to figure out what exactly it is. So it says 12.5 grams of helium gas fills a balloon up to 2.5 liters. Well, we know we have a volume. If 3.18 grams were taken out of the balloon, what will the new volume be? Okay, so I know that's a 1. I know I'm looking for V2. Now, so this is an N. Now remember, in Avogadro's law, it's the N can be grams or moles. So we're going to put 12.50 grams. And our N2 is 12.50 minus whatever was taken out, which in this case comes out to be 9.32 grams. Okay, so our N1 over V1, so it's 12.50 over 2.5 equals 9.32 over V2. Once again, we cross multiply and divide. So we get 9.32 times 2.5 all over 12.50. And when we do that math, we end up with 1.86 liters. What size container, that means volume, will 36.05 grams of argon gas fit into at STP? Okay, you have a volume and an amount and an STP. That means there's two things you can do. There's two ways to work this problem. First thing you can do is you can use the mole bridge, or you can use the ideal gas law. So I'm going to show you both ways. Okay, so first we have 36.05 grams of argon. Now we got to put the molar mass in here. And then we put the molar volume in here, which is 22.4 liters. And this gives us 20.2 liters of argon. Okay, that's pretty easy, but some people are still not comfortable with picket fences, so they would just rather do the PV equals nRT. Okay, standard pressure is 1.00 atm, and N is 36.05 divided by 39.95, which is 0.902 moles. Okay, our R value is 0.0821, and our temperature is 273 Kelvin. Now our equation, because it's volume equals, you should have all of these ideal gas law equations written on your sheet. Okay, so volume is 0.902 times 0.0821, 273 all over 1.0, and you get 20.2 liters of argon. Either way you look at it, you get the same answer. Doesn't matter which. Okay, number 11. Okay, so at what temperature is a 59.87 gram sample of argon gas if it takes up 1.54 liters at 1.02 atms? Okay, it looks like we're asking for temperature, and so let's write that down. So it's looking for temperature, which means degrees Celsius. We have a mass, which we're going to be converting to moles most likely. We have a volume, which is 1.54 liters, oops, and a pressure, which is 1.02 atmospheres. So our N value here is going to be 59.87 divided by, okay, it's argon gas again, so we can do the 39.95. And that gives us 1.50 moles. And now our pressures in atmosphere, so our R value is 0.0821. We want T. We know that T is PV over NR. So T is 1.02 times 1.54 divided by 1.50 and 0.0821. When we do this, we get 12.8 K or 13 K. So I'm going to go ahead and write it 12.8. I'm going to cross this out. So it's 13 K minus 273 gives us negative 260 degrees Celsius. It's a negative sign in there. Pretty darn cold. Really, really cold. 13 K is getting close to absolute zero. Don't think it's going to happen on this earth. Well, it could, but most likely not. Okay, number 13. What is the molar mass of a gas that has a density? So we're looking at molar mass and density. So we're already looking at, and it wants the molar mass. We're looking at the dirty P equation. So it wants molar mass. It has a density of 0.946 grams per liter. Now, we have a P and a T. That's 1.0 atmospheres. Oops. ATM. And 273 Kelvin, which means we have an R of 0.0821. So, molar mass equals 0.946 times 0.0821 all over 273 at 1.0. When you do this, you get a molar mass of 21.2 grams per mole. Pretty easy, right? Hopefully. Okay, number 14. What is the density? So we're looking at dump dirt. Don't even have to go any further because it's the only one with D. What is the density of carbon dioxide? So I'm going to need a molar mass. So CO2 is 44.01 grams per mole at 1.02 atmospheres and 25 degrees Celsius. So we're looking for a D. We have our molar mass. That's 44.01 grams per mole. We have a P. P is 1.02 ATM, which means our R is 0.0841 or 21. Oh, I wrote 4. And then our T is at 25 degrees Celsius or 298 K. So D equals 44.01 times 1.02 all over 0.0821 times 298, and it's 1.83 grams per liter. Now guys, if you don't know all the units that go with each of the letters, like you don't know density is supposed to be in grams per liter, you might want to write that down. Okay, our next section is gas stoichiometry. Back to the picket fences again. That's what we did yesterday. So hopefully you guys understood this. If not, well, there's only a couple of gas stoich problems on the test, but they are worth quite a bit, so get help. Okay, so let's look at number 15. What volume of octane is needed to produce 15 liters of carbon dioxide at STP? Okay, so when you're talking about gas stoichiometry and you see STP and it's volume to volume, if you remember, that's the simplest one. That's kind of like going from moles to moles. because you use a volume ratio rather than a mole ratio. It means the same thing. It's just you put the L there instead of mole. So we're going to start out with 15 liters of CO2. And when you use your equation, find CO2, it's 16. So 16 liters of CO2. And we're looking for C8H18, and that's a 2. C8H18. Oops, don't need that last line there. And sometimes you'll do that. Put an extra picket in there when you don't need it. This comes out, this comes out. 15 times 2 is 30. 30 divided by 16 is basically 1.9 liters of C8H18. That's the easy one. Okay, let's look at 16. What volume of oxygen is needed to react completely with 125 grams of octane? So this is a mass to volume. Okay? So mass to volume, we have to go from mass to moles. And then we put it into the ideal gas law equation. So we're going to start out with 125 grams of octane, which is the C8H18. Now, we have to go from grams to moles. So we have to divide by the molar mass, 114.26 grams of C8H18, 1 mole of C8H18 is. And then we have, which from the equation, so we have 2 moles of C8H18, and then if you look at the equation for oxygen, it's 25. So it's 25 moles of O2. Make sure our units cancel out, and that gives us our N value. So of 13.7 moles of O2. Now this is N equals. So we're looking for volume. So we have a T equals, now the T is 27 degrees Celsius, or 300 K. We have a P, our P is 103.3 kPa, which means our R value is 8.341. So I think we have everything. Yep. So now we're going to do it, and remember the equation is this. So V equals N, which is our 13.7, make that better, and R, which is 8.341, and T, which is 300, all over 103.3. Okay, so when you do this, you get 331 liters of O2. Ooh, that's an awful lot of O2. Okay, last problem, 17. How much grams, so we're ending up with mass, of water is produced if 87.4 liters of carbon dioxide are produced at STP? Okay, so we're going to start out with our liters. Now this is a volume to mass, so we have to use the ideal gas law to find our number of moles. So in this one, we're looking for our N, and we have our pressure, which is 1.0 atmospheres, which means we have our R value, 0.0821, and we have our volume, which is 87.4 liters, so PV&R, and our temperature, which is STP, which is 0 degrees Celsius, or 273 K. Okay, now remember our equation is N equals, what is it? N equals PV over RT. So N equals P, which is 1.0, V 87.4 over R 0.0821 over 273. And when we do that, we get 3.90 moles of CO2. Okay, now we're going to use that to put into our picket fence. Now we're going from moles of CO2 to moles of water, so we have to look in our equation. This one is 16 moles of CO2, moles of water is 18. And we know 1 mole of water has a molar mass of 18.02 grams. And when you do 3.9 times 18 times 18.02 divided by 16, you get 79.1 grams of H2O. Okay, hopefully that's helped you. If not, come see me after school. We're going to have a review session Thursday after school. Come see me after school any day, Wednesday if you want, tomorrow, whatever. It doesn't matter. Just come see me after school or in wrap. Well, I don't have a Thursday wrap, but I have a Wednesday wrap and a Friday wrap. Well, if you're in first or third, that's kind of too late, but just come see me. Okay, so everybody have a good night, and I'll see you tomorrow. Bye.